Hello everyone, and welcome to our presentation of Mahindra's journey to defining the dimensional engineering process. My name is Steve Bannasch, and I am the Chief Engineer for Dimensional Engineering and Quality for Mahindra North American Automotive Division. I have been involved in dimensional engineering for over 30 years, and I have traveled the world helping companies set up dimensional engineering groups. I would like to thank DCS for giving me this opportunity to share our journey at Mahindra with you, and I hope you find the presentation helpful in setting up and improving your own dimensional engineering process. When Mahindra first started the journey of creating a dimensional engineering group, the first question that we asked was, what is the function and role of dimensional engineering, and how does it add value enhancement to the entire Mahindra ecosystem? One of the biggest problems facing us was there is no one true definition or understanding of the role of dimensional engineering. While researching our own ecosystem of product development, manufacturing, and quality engineering, as well as our external suppliers, it became apparent that there was no one true definition or understanding of the role of dimensional engineering. Each engineering area and supplier had their own definition of the role of dimensional engineering, which provided no consistency of the work being done. With just a quick internet search of other OEMs and suppliers, we saw that there are many different definitions of dimensional engineering and that there is no one clearly defined dimensional engineering process. To create commonality across the entire Mahindra ecosystem, Mahindra developed its own definition of the role of dimensional engineering. We settled on dimensional engineering is the scientific approach of product and process development, utilizing the PDCA process of step-by-step improvements to achieve milestone targets through experimentation with the goal of establishing a stabilized product and process design with built-in quality that eliminates hidden waste and cost. It's a long definition. We feel it encompasses everything we've asked for. The most important takeaway we found when we were establishing our common process is we needed to address what we called the elephant in the room. While researching our own ecosystem and asking our own internal engineering groups, external suppliers, and how they define dimensional engineering, it was clear that there was one consistent response. Dimensional engineering is GD&T. While we won't get totally into it, we felt it was very appropriate for us to define that dimensional engineering is not GD&T. We need to make sure that that's clear and everybody understands it. Geometric dimensioning and tolerancing is a symbolic language used by the dimensional engineer to communicate to all engineering ecosystems the allowable amount of variation from their specified datum targets. It is the maximum amount allowed to provide for a repeatably controlled and stable process. As a starting point, we decided to look at Mahindra as a series of separate programs working in unison to fully benefit the organization. A program can be defined as a refresh of a product, the addition of new accessories, a new product entirely, a quality or continuous improvement program, or etc. From there, we decided to focus on one single program and break down the processes involved in driving each program. Looking inside each program, we clearly defined three processes that drive each program to satisfy and support the program goals and objectives. The three processes are the APQP process. The APQP process describes how customer needs and expectations are linked to planning and defining a quality program. A product development-centric process with the support of manufacturing and the quality communities. Lean. Lean is concentrated on the plant and product production layout, establishing a philosophy and a system of interconnected processes and people working to continuously improve how they deliver value to the customers. The main focus on Lean is on the manufacturing plant layout and throughput. Last, Six Sigma. Six Sigma is focused on well-defined projects that have a direct impact on specific defects. First, we really wanted to understand AIAG. So the Automotive Industry Action Group, AIAG, has established the APQP, Advanced Product Quality Planning process, to reduce the complexity of product quality planning for customers and suppliers by allowing customers to easily communicate their product quality planning requirements to their suppliers. It is a structured method of defining and establishing the steps necessary to assure a product satisfies the customer. AIAG has published additional supporting standards to ensure the commonization of product and quality planning. The importance of the APQP as it relates to lean is that the product is designed with built-in quality that accommodates manufacturing and quality limitations. Next, lean. The second process we're all familiar with. Toyota Production System is the frame for what is often called lean management and has been embraced globally as the standard for plant and production layout. The importance of lean structure is that in order to improve the house must be built on a solid foundation of stability. The stability is rooted in the built-in quality of the product design and quality from the APQP process. Third, Six Sigma. Six Sigma is focused on the control and improvement of variation in very specific, clearly defined problem areas which contribute to large swings in variation and need improvement. Very specific and clearly defined micro projects as we define them. Similar to the PDCA of APQP and Lean, Six Sigma is based in the DMAIC, Define, Measure, Analyze, Improve, and Control process. It is important to note that each one of these processes is circular and continuously builds on a learning cycle of rotation. To illustrate the PDCA and the DMAIC processes, rotation, we view them as gears driving the program. We add in the APQP, we add in the Lean, we add in the Six Sigma. When we've added all of these gears into our program, what we've noticed is they are all working, but they are all working independently of each other. APQP is a lot of stuff going on in product development, Lean is working inside the plant, and Six Sigma is focused on strategically reducing specific programs and variation and control. So enter the dimensional engineering process. The dimensional engineering process unites all three processes and increases the overall efficiency and effectiveness of the program, leading to shortened development cycles by identifying and eliminating waste and cost throughout the entire development process. Note, the dimensional engineering does not encompass all the work of each one of these processes, but provides a driving link between all three. So, when I've added all three and put a dimensional engineering process in place, we find that now the system is working. Once we have our gears and processes in place and we understand how they're working, the next question we have to ask is, how does dimensional engineering integrate all these processes and disciplines to eliminate waste and increase built-in quality? Utilizing the APQP and the product quality planning timing chart, Mahindra has developed its own Mahindra product development system. While it may look different to your organization's development process, we have found that all suppliers and OEMs development system has some roots in the APQP process as displayed. The key milestones being concept initiation and approval, program approval, prototyping, pilot, and launch. The feedback assessment on the bottom and corrective action loop are the key to the dimensional engineering interaction. Throughout the Mahindra product development system, dimensional engineering utilizes the scientific thinking approach of PDCA and DMAIC. The scientific thinking approach is driven by fact-based, data-driven, iterative learning. The steps to the PDAIC and the DMAIC are simple and straightforward. 1. We make observations and we set targets through benchmarking and prototyping. 2. We question the ways to improve process and/or design. 3. We form a hypothesis on how to improve. 4. We conduct a simulation based on our hypothesis and set targets and goals again. 5. Test the simulation results in prototype build. Last, we use all these results in the simulations of prototype to make new hypotheses and new simulations to improve. As stated earlier, the product development system for dimensional engineering, we are going to follow the PDCA. We have now defined the PDCA of dimensional engineering inside of Mahindra and how it works within that system. Plan and define. We focus on benchmarking vehicles and benchmarking processes from competitive vehicles and our own internal vehicles. We set targets for each one of our build events and we monitor them. Do. Tolerance studies based on design and proposed manufacturing processes. We review supplier capabilities. We establish a coordinated datum strategy. We establish weld and fastening sequences. and we establish measurement plans to support all our expectations. Check. We do a thorough review of all fixture designs. Check fixtures, manufacturing fixtures, and all to ensure coordination. We measure every piece and subassembly through the entire prototype and production build. We then root cause of any unexpected results and provide corrective action. Act. Institute corrective actions for the next build. Planning for the next cycle can proceed with a better baseline. So this is again a circular rotation that we follow through every single milestone phase as described at the APQP and Mahindra product development system. Before we proceed, we now need to understand what are the dimensional engineering tools in the engineering toolbox. Everyone has heard the saying, the right tool for the right job, and you are only as good as your tools. Both sayings are true when it comes to the choice and application. Knowing when and how to apply the right tool is the key. The dimensional engineering tools are datum coordination. Datum coordination is the most important tool in the toolbox. Datum strategy will tie design, manufacturing, and quality processes together. The foundation of standardization and stability within our whole system is based on datum coordination. We benchmark competitive vehicles for their fit and finish. We review their manufacturing processes. We review their material selections. We understand their subassembly and joint concepts for fastening the process. Fixture designs. Ensure that the fixtures match datum structures for stability. Establish gauge R and gauge R&R capability. Ensure that all fixtures are repeatable and will produce desired results that we are looking for. And 3, we work in establishing clamping and fastening sequencing. Clamping and fastening sequencing is often overlooked in fixture designs, but as the clamps and fastenings go down, you move variation in certain ways, and we need to eliminate as much as possible. Last, the DCS software suite, which is what we're here to talk about. Using the DCS software suites to ensure datum coordination and maximize tolerances that support the entire ecosystem goals with a focused analysis on characteristics most likely to impact product and production performance while coordinating the collection of measured data. Moving into the APQP Mahindra product development process. Now we have defined our plan, do, check, act of every milestone. Moving forward, we will walk through the iterative process of PDCA. Entering the plan phase. At the earliest part of the planning stages, we need to recognize and accept that variation can come from many different sources. Our goal is to identify as many sources of variation as we can as early as possible. As variations are identified, the dimensional engineer needs to establish controls to stabilize and manage them. Variation is measured and recorded using SPC data. As variations are identified, the dimensional engineer needs to use his tools to stabilize and reduce common causes of variation as early as possible in design and manufacturing process. Additionally, it'd be wasteful to continually collect data and document processes from previous programs and not learn from it. Utilizing historical data from the QDM database as the starting point for product design and manufacturing development, the dimensional engineer will work between the design manufacturing groups, the iterative process of tolerance analysis utilizing design and manufacturing concepts. Last in our planning phases, the dimensional engineer participates in benchmarking of competitive vehicles to review the manufacturing processes, the fit and finish, and material, and the customer review and expectations. The output of the planning stage we have clearly defined. We will have design goals for each phase, build, reliability and quality goals, a preliminary BOM, preliminary process flow, preliminary special characteristics, establish DTS targets and objectives. The next step leads us straight into the do phase. In this step, the dimensional engineer will work between design manufacturing groups to start the iterative process of tolerance analysis utilizing design and manufacturing concepts. The dimensional engineer uses a set of design for manufacturing and design for assembly principles. The importance of the DFMA is underlined by the fact that about 70% of manufacturing costs, that's cost of materials, processing, assembly, are determined by design decisions, while production decisions, such as process planning or machine tool selections, are responsible for only 20%. Design for manufacturing and assembly is a simultaneous engineering process designed to optimize the relationship between design function, manufacturability, and ease of assembly. Note that 5% of the process is contributed to labor and 5% is contributed to overhead. While working between the product, manufacturing, and quality groups using the DFMA principles, the most important tool for a dimensional engineer to manage and control variation is the datum strategy. Datums are the connective tissue that provides one common link for data across the entire ecosystem. Product engineering uses datums to design and fabricate. Manufacturing uses them to locate and assemble, and quality uses them to locate in their check fixtures and collect data. The importance of datum logic cannot be stressed enough. These are the binding tissues between all three development groups. At Mahindra, we have decided and followed the ownership of the datum strategy is the responsibility of the dimensional engineer. During our research to define the dimensional engineering process, the ownership of datums was a controversial topic, and each group claimed ownership. Product engineering, manufacturing, quality, and even some of the suppliers stepped forward and said that they own the datums on their products. While all groups agreed that datums were selected on their functionality, what defines the functionality? When one part was given to each group, everyone came up with a different datum scheme that focused on their own specific needs and not the programs. To ensure connectivity and standardization, the dimensional engineer is now responsible for collaborating and working with all these groups to establish a common set of datums to ensure coordination. Once we have established a MBOM and a preliminary datum strategy, as previously discussed, the applications of tolerances are developed from previous programs and lessons learned. Using benchmarking in the QDM database, preliminary tolerances are applied. We are building on previous knowledge. So we do not automatically start assigning values and start calculating. We are actually scientifically going back on everything we have learned and building on those learnings. From the preliminary MBOM, datum strategy and tolerances, the dimensional engineer using a CMM macro developed at Mahindra now will go and place the CMM measurement points inside of the CATIA model. Each point is named, the tolerances are applied to the point, and the XYZ coordinates are maintained inside of CATIA. By managing and placing of the CMM points, there is a consistency and provided coordination through the DCS model simulation to the measurement process. Points are placed opposing and normal to each other on every meeting assembly to ensure coordination. Additionally, CMM points are then loaded into the QDM database for ready access for all suppliers to download and input into their own CMM program. This saves a tremendous amount of time, money, and ensures our coordination. Next, the 3D simulation will begin, and Byron Hamm from our group will provide you with a short overview of how we did the simulations.
Hi, my name is Byron Hamm. Today I'm going to show you how we can input QDM data into a 3DCS model. As you can see on the screen, we currently have a model that has points around the edge of the door opening. These points correspond to CMM points that are in the program. The names are the same as would be in the program. These currently have tolerances based on the GD&T sheet provided by the dimensional engineering team. Currently, they are at plus or minus a half. What we would like to do is replace these tolerances with actual CMM data taken from the plant. Later, you will see how this data is exported from QDM Web. In order to get these points into the model, first we have to create a tolerance. We want to select a user DLL. Click Add, and then the dialog screen comes up. We'll give it a new name, in this case body and white CMM data, and then select a user routine. In this case, we will be using the DCS TL CMM DV2. What we need to do is connect the file that came from QDM to this tolerance. To do that, we have to select the More. From this dialog, then we select Strings, and then from this dialog box, it's asking for the path to the file. So click on Add File Path, and your file folders will show up, and connect it to the QDM output file, which in this case is the U321 body and white less doors. that was provided. Hit open, hit OK, OK again. So this will link the CMM point data to the tolerance. What we have to do now is specify which points we want those to be on. So we have to select add, and then we select all the points that we want the CMM data to be connected to. In this case, we're going to select all these points. Once this is done, you can hit OK. And you will see the CMM points will be in here. Currently, everything is inactive. If we activate all, now you have the CMM data attached to these points, but we also still have the original tolerances. So we have to deactivate these two so that they don't influence the CMM or the simulation data. If we run a quick simulation, you will see that the body and white CMM data is showing up in the high-low mean in this location. This shows us how we can replace current tolerances with actual CMM data from the plant for providing us new information on analysis.
Thank you, Byron, for that presentation of the 3DCS models and how we are using them. After we've done our do part of the 3DCS model and tolerance analysis, we now are going to move into the check phase. Working with the quality groups to collect data, the dimensional engineer will review the data collection processes and begin to root cause the sources of variation in each prototype build. But before we can build or measure actual parts, we need to ensure that the fixtures and the measurement processes are in agreement with the datum structure and the measurement plan. Utilizing the MSA and PPAP manuals from the AIAG group, the dimensional engineer will ensure and participate in a gauge R, a gauge R&R, and a tool repeatability study for all check fixtures and assembly fixtures. The dimensional engineer will participate in all design reviews and buy-off before construction of both types of fixtures. This is to ensure that we are actually following the exact datum strategy that has been developed and put into the CATIA models for all fabrication and product development sources also. As we have discussed in the previous steps, utilizing the QDM database historical data, we establish preliminary tolerances. Our next step is to start collecting data from our prototype builds and use it to input into the QDM. So now, let's take a look at QDM and how we are using it. The Quality Data Management System is a modular quality system that collects and standardizes and analyzes measurement data to deliver real-time insight into production quality. QDM, one of the things it does is it provides coordination. Utilizing QDM, we are now able to manage the placement of all of the CMM points in CATIA and ensure the coordination between our 3DCS models, PPAP, and process checks. As we put the points in CATIA, they are then exported and put into QDM for all suppliers and measurement processes to use. This ensures that we are maintaining our coordination through every single build and all the way through the final process. Tracking. By managing the points through the process, we are able to track the same exact point from build phase to build phase. Enable us to track improvements due to design and or process changes through each build. As we change sequencing of clamps, sequencing of fastening devices, as we've made design changes, we are able to use the same exact point and monitor it to gauge the impact of the changes we've had from the previous build. Accountability. Accountability allows us to track and maintain the accountability of our suppliers and our in-house plants. The program will automatically send out notices of data due to match our control plans. Accountability is always a tough situation to call. It is not to be used as a punishment against any supplier or internal supplier. It just makes sure that we are all holding ourselves accountable as a team to making sure that we are measuring our parts and we are actually getting them as close as to print, if not to print. This is all part of the process improvement, and it is not, I have to keep expressing, not a part of any type of beating up or browbeating of anybody in particular. It's just holding the team and the development team to a standard of excellence. Standardized reports. Instead of receiving reams of measured data in numerous formats, all reports are standardized so that the ease of reading them and following the data. By allowing QDM to accept the raw data from all measurement equipment and putting into a format similar or it's standardized against everybody else, allows us to interpret the data, read the data, all in a similar fashion at the same time. Unique source of information. The QDM is centralized cloud-based or web-based. It allows us to log in from our iPhones, iPads, computers, anywhere in the world to review. The beauty of the whole part is it is the same data all the time. So when somebody logs in and you are having discussion, you don't have to ensure that everybody's looking at the same data or if there's been different processes. It is all the same. So having it centralized in one unique location, having a meeting and logging in, the data is straight in front of you and there is no more, that's the wrong data, this is data. We all have it up to date and we are all talking about the same data. Real-time monitoring. Real-time monitoring is still in process with us at Mahindra, but we are in the process of moving QDM onto the data collection machines on our floor. QDM is a database and it has the ability to gather any type of measured data. We are in the process of connecting all measurement equipment on our floors to the QDM so we can now actually send off immediate alerts as to when processes are beginning to become unstable or out of control, meaning that we are going to trigger a reaction of how to adjust. Now, let's go to a quick demonstration from Kastriot Cupi on how the QDM system is being utilized inside of Mahindra.
Thank you, Steve. On this short demo, I'm going to focus only on some of the applications and functions of the QDM web database, such as data sorting, reports exporting, and integration with 3DCS. When logging in into QDM web, you are presented with a data navigation page. It allows you to sort through the data stored into the QDM database in an intuitive and straightforward way. You can go through the drop-down menus here on the left side of the interface, or you can search directly by subsystem, inspection program, sequence name, and so on. For this particular case study, we need some real manufacturing data for the body and white assembly of one of the programs we have worked on. We're going to use that production data to update our 3DCS model used during the product development phase by replacing the predicted tolerances with the actual production capability. QDM Web can help us do that. Here on the left, we can go through the data and find the assembly we're looking for. First, we select the company, in this case Mahindra India, then product type, body and white, the plant where the part is being manufactured, Nashik, the program, U321, which is the program code used by Mahindra, the data source, it's autofilled because it's the only data source available for this program. Subsystem is body and white, and finally the inspection, which is body and white assembly less doors. As I mentioned earlier, we could have also find this data quickly if we knew the inspection number, which at Mahindra is always the production part number. A simple search by inspection would have gotten us to the same point where the drop-down menus did. It is of course possible to filter the data by date, in case we want to focus on a particular month, week, day, or even hour. The system will show the samples available and we can select as many as we want. I'm going to select all 5 samples available in this case. It is also possible to generate automatic reports that will be shown in the standard reports section. At Mahindra, we have set up the system to generate automatic reports for the last 5 samples for every inspection available. This can save you some time if you're interested in having a quick look at the latest data available without having to go through the sample selection and report generation process. We also use this section to store other documents pertinent to the part, such as measurement point CSV files that, like Steve mentioned, can be downloaded by suppliers and imported into their measurement programs. Measurement roadmaps, PPAP documentation, control plans, etc. All available in one location, accessible from anywhere. Going back to our user case, after I select the samples I'm interested in on the filter data section, I can generate the report by clicking Generate Report here on the right side of the screen. It will open a new window that will allow you to configure the reports the way you want, by choosing the output format and by filtering the data. For the purpose of this demo, we're going to export the data I selected in a 3DCS compatible format by selecting it from the output drop-down menu here on the bottom left. After you click Generate Report, a CSV file will be downloaded onto your local drive and can be later imported into the 3DCS model, as Byron showed you earlier in the presentation. As you can see, if you open it, the CSV file contains all the points that have been measured, their X, Y, and Z coordinates, their specification limits, IJK vector, and of course, their actual measured values. Going back to the QDM web report page, it is worth taking a look at an interactive report created by the system. To create one, you just have to select Interactive Report from the Output Type drop-down menu and hit Generate Report. The first few pages, depending on the total number of the measured features, is allocated to the measurement points roadmap. Each circle tells you at a glance on which page the trend chart is located, and more importantly, if it is or it is not out of spec, based on pre-assigned criteria. Scrolling through the report, you can then see the chart pages that can be personalized to your needs. Every chart points to the exact location in the CAD data, so you always know immediately what feature you're looking at. They also are expandable by simply clicking on them to access more details. Of course, these are only some of the scenarios Mahindra is using QDM Web for. Over the past few years, it has become a key partner on our journey to achieve our quality goals. Thank you. Back to Steve.
Welcome back. Thank you very much, Kastriot, for that demonstration on how Mahindra is using the QDM system. Once we have completed the plan to check portions and we have loaded our data from the check into the QDM database, we are now moving on to the act phase. In this step, the dimensional engineer will work directly with the respective quality groups to ensure the data collected and processes have been adhered to. Using the data, the dimensional engineer will then begin to evaluate and root cause the sources of variation in each prototype build. As always, the first step is to ensure the datum strategy is supporting the program. By reviewing the gauge R and gauge R&R data, we ensure that we have a robust datum strategy. Capability is the foundation of the program, and moving forward with a robust datum locating strategy is critical to the success of the program. Once we have determined that we have a stabilized datum strategy, each joint of every assembly will be reviewed to ensure that all detail level parts meeting tolerance specifications can be loaded into the assembly fixture and properly located without any manual manipulation. Parts and assemblies should not introduce any stress into the fixture and assemblies that will adversely affect the location of critical features. At the earliest stages of the design, the product engineer typically begins with a nominal design that shows no design gaps. Given the fact that we have already acknowledged that variation exists, we know that there is no such thing as a perfect part and/or process, and the design needs to provide allowances for tolerances without degrading the structure of the design. Without design gaps, there is an assumption that if all parts and assemblies meet all GD&T requirements, they will assemble without manual manipulation. By reviewing each joint concept of the vehicle, the dimensional engineer will begin to add small design gaps based on all the anticipated and measured variation. The gaps are intentional and deliberately added to the design to allow parts and assemblies to fit together in the fixtures without causing additional variation to the critical features. Working with the manufacturing engineer is important to stress the weld and fastening sequences at this point. Geospots are put in place to ensure the stabilization of products before they move to another fixture. Once the process and parts are stabilized, we can now focus our attention on the fit and finish. As stated earlier, through the design and prototype build processes, the dimensional engineer is constantly working to reduce variation to meet the fit and finish targets. Throughout each prototype build phase, All of the following are under constant scrutiny: the fastening sequence, the fastening methods, joint design and configuration, assembly sequences, piece part tolerances. Tolerance simulations and analysis are continually updated with that information. At SOP, if all processes and parts are stabilized and repeatable and we have still not met our DTS objective, the team is now faced with some serious decisions. Do we take the time to look for different processes that may cost more time and money to achieve our objective? Do we tighten tolerances on specific parts to allow us to meet our objectives that once again will cost time and money? Or do we change the DTS to match the capability and then allow the Six Sigma group to come in and continually refine in specific areas, thus updating our DTS to the predicted and controllable results that will be different from the original target? The reason we would do that is to ensure that the plant is not held responsible for DTS objectives that are unachievable at this time. As you can see, we consider the dimensional engineering process to be an iterative process that builds on itself throughout the design and prototype phases. The key is being able to plan, do, check, act for each milestone and continually checking the results versus what you had anticipated to have happening and making corrective actions. One of the bigger keys of the whole plan, do, check, act, as we've set it in place, as you can see, is as it builds upon itself going up that hill and gets to SOP, the next program behind it does not start again at VP0, but it only picks up the data that we've learned from our previous experiences and applies it to the next program. This is what we consider a continually building on itself process, and this is the direction that we are headed at Mahindra. Thank you for your time and patience. Hopefully this has been informative for you, and we look forward to talking to you.